Calculus. Today we are going to talk about polar coordinates. And so today is going to be more of a pre-calc review of the idea of polar coordinates and polar equations. And then in our next lesson, we will look at how to bring calculus into those ideas. So polar coordinates, instead of being an x comma y, are defined as an r comma theta, where r is the distance from O, which is the origin, to the point, and it's a directed distance, so r can be negative. And then theta is the angle from the initial ray, which is the positive x-axis, to the point. And we go counterclockwise when we measure those angles. So this is a picture of our point, r comma theta. So that initial ray, again, is that positive x-axis. And then we go counterclockwise theta degrees and go out a distance of r from the origin or the pole. And that gives us our point, r comma theta. So here's some examples. That point at the end of that segment then could be named actually infinitely many different ways, but here's two different ways that we could name it. We could say that we've gone positive pi 6 as our angle and out a radius of 2, but if we went around the other way around the circle and we went around clockwise, we would have gone negative, because that's the negative direction, 11 pi over 6. So those 2 points, although they have different values in them, actually define the same point. So polar coordinates are not unique. So then we can also have negative r values. So that point that is labeled, again, that dot, we could say has a positive r value of 2, and then that would be at the 7 pi 6 angle. Or we could go to the 1 pi 6 angle, but then go backwards 2 from there, and that would put us along that same line. So because the pi 6 and 7 pi 6 angles lie on the same line, a positive r would put us in one direction, but a negative r would put us in another direction. And we'll look at some examples of how we can convert between xy points and r theta points for some practice with this negative r idea. Okay. And again, here's another picture of just how the same point can actually have many different names. So we could go positive pi 6 and positive 2. We could go positive 7 pi 6, but then we'd want to go backwards, so that'd be a negative 2. Or we could go backwards angle and go negative 5 pi 6 and backwards direction, negative 2. So lots of different ways we could name it. Those are just 3 options, but really there's infinitely many different options of ways to name that point. Some important simple polar equations. The equation r equals a number is going to graph a circle for us. R we can think of then as radius. Gives us the radius of the circle that's centered at the origin. So here's some inequalities. In that first one, we have an r value, or a distance away from center value, of between 1 and 2, and theta values between 0 and pi halves. So that tells us we're only looking in the first quadrant, and then the points that are between 1 and 2. So it's like a quarter of a donut there. In B, a theta equals equation defines a line. And so theta equals pi force defines that line at the 45-degree angle, the pi force angle. And then since r is limited between negative 3 and positive 2, that gives us the distance of either negative 3 direction or positive 2 direction. And so it gives us a line segment. And then that last one, with our theta being between 2 values, we get each theta equation would give a line, and then being between that shades the area between those 2 lines. So these equations are going to be our equations that we're going to use to convert back and forth between r's and r theta and x comma y. And we're going to do a few example problems where we convert our equations back and forth between xy equations and r theta equations. I'm going to, when I switch over to my writing board, I'm going to show you where these equations all come from, so that it won't feel as much just like random memorization or, oh, I always have to look those up. Once you see a picture of where these come from, you probably won't even need to look them up when you need them. You'll just be able to define them from the picture. So this is the picture, but I'll draw it out again so that I can label some stuff. So this is our picture of x and y there, defining a point as x is over and y is up, and then theta being our angle and r being our distance there. And so what you can see we end up with is a right triangle. So all those equations come from right triangle properties. All right, and that example we're actually going to do. So let's switch over to that whiteboard. All right, so for our first problem, let's go ahead and look at how we can switch between points of r theta into a point of xy. So if I have an r comma theta point defined as -4 pi, I want to turn this into an x comma y point. So I'm a really visual person. So I'm going to graph this out. So if my theta angle is pi, then I need to locate pi on my unit circle. So I got pi over there. But then I'm going to go a -4 from that pi. So I'm actually not going to head towards the pi, -r. So I'm going to head away from the pi. So this is our point over here that has a distance of -4 on the theta angle line. So then what is that point for x comma y? That point is 4, 0. X is 4 and y is 0. Let's look at another one of these. Let's say our r comma theta is equal to 6, 7 pi thirds. Okay, so I'll start with the angle again. So 7 pi over 3. All right, well then I'm thinking about cutting this into pi thirds. Well, 6 pi over 3, that's 2 pi. So 6 pi over 3 would take me all the way around the circle, and then one more third of pi. So my angle is actually like this. I went all the way around 6 pi thirds and one more. So that's my 7 pi thirds line there. And then I want to go out a distance of +6 along that. So that distance is 6. Now, if I make this into a triangle here, it's on really a pi thirds because it was 1 pi thirds past that 6 pi thirds. So pi thirds is 60 degrees. And our 60 triangle is usually 1, 2, and square root of 3. But our hypotenuse on this one is 6. So everything has a multiplier of 3. So we got 3 root 3, and this side is 3. It's like we took that 1, 2 square root of 3 triangle and just blew it up 3 times as big. So then now my x comma y is going to be x is 3 and y is 3 square roots of 3. Okay? So use some special triangles there, 30, 60, 90, 45, 45, 90 could come in, and then the unit circle there as well. We can convert the other way as well. So let's say that I have a point that is an x comma y point, and let's say that it is -2, 0. Okay, now we actually have to be given some restrictions as well because polar points are not unique. So there's infinitely many different answers that we could give here. Now that doesn't mean every possible answer you could come up with and make up any numbers you want is right, but there are infinitely many right answers to this question. So to specify down, we're going to give some restrictions that also say that r has to be negative in this problem, and that theta has to be between -pi and +2 pi. Okay, so again, I'm a picture person, so I'm going to plot that point. X is -2 and y is 0. So there's my point. Okay, so if I want r to be negative, then I'm going to say that r is -2 because we're talking about distance from center. So I'm going to say that r is -2. But if r is -2, then I don't want to name the angle line that it's actually on. I want to go the other direction. And so this is our angle line, which is the 0 line. Looks like it kind of froze on me there. 0. There it is. And then it could also be 2 pi. Maybe I shouldn't have included an equal to bar on that, because then 2 pi would also be a right answer to that question as well, but we'll just leave it at the 0. Okay. One more of these. Let's say that my x comma y point is square root of 3 over 2 comma 1/2. Once again, I want r to be negative, and we're going to use that same restriction. So we're going to say between negative pi and 2 pi for theta. Okay, so I'm going to start by plotting that point. So x is positive square root of 3 over 2, and y is a positive 1/2. All right, so now I have my point defined out here. And so what I need to figure out is how far is that point away from 0, and what angle am I at? Okay, so what I'm going to do, just because the way that I have the triangles memorized, I'm going to get rid of those 2's in there. And so I'm going to say, well, my normal pattern I think of as 1, 2, and square root of 3. Okay, so this triangle has been like half sized from that normal pattern. So that would mean that that length along that r line is 1. So r is going to be 1, except we want r to be negative 1, which means that instead of naming that angle, we actually want to name the angle that's going out the other way along that line. So then what is that angle? Well, in that 30, 60, 90 triangle, opposite of the 1 should be a 30-degree angle. So if we go out the other direction on it, that'd be 30 degrees, or that's a pi 6 past our pi line, or 6 pi 6. So that is 7 pi over 6. 7 pi over 6 is between negative pi and positive 2 pi. Okay, so we can switch back and forth between points of r comma theta and x comma y. And then now let's look at how we switch back and forth between those equations. So that picture I said I was going to draw up for you of the relationship between x, y, and r theta. So theta is an angle, and r is the distance from the origin. And then x is horizontal and y is vertical. So there were 4 equations that tell us about how polar and Cartesian, or xy, coordinates relate to each other. And they all come from the fact that we just made a right triangle. So first right triangle equation that might come to mind is Pythagorean theorem. X squared plus y squared equals r squared. So that's an equation that relates x and y with r. And then the rest of them are going to come from trig. So right triangle trig, the tangent of theta, tangent is opposite over adjacent. So the tangent of theta is y over x. So that relates x and y to theta. So those 2 equations would help us if we have x's and y's and are trying to turn them into individually r's and thetas. Our other 2, well, let's do our other 2 trig equations. So if I have the sine of theta, sine is opposite over hypotenuse, so that'd be y over r. We typically rewrite this, and so we're going to say r sine of theta is equal to y. So that relates our r's and thetas with y. And then likewise, cosine is adjacent over hypotenuse, and so then if I multiply by the r, our cosine of theta is x, and so that relates our r's and thetas to x. So those 2 equations would be helpful if we know r and theta and are trying to individually turn them into x's and y's. So let's look at an example where we want to change an equation from x's and y's into r's and thetas. So Hopefully you kind of recognize this equation as being the equation of a circle. So it has an x squared and a y squared, and that's equal to radius squared for an equation of a circle. This has a shift on the y-axis. Y minus 3 is going to take that circle, move it up 3 spots. So if we turn this into an r and theta equation, what I'm going to do is start by squaring out that binomial. So that's going to be y squared minus 6y plus 9 if I multiply y minus 3 times itself. Now I want to look in here for anything that's in those 4 equations where I can make a substitution. So one place I see that I can make a substitution is this x squared plus y squared. Well, x squared plus y squared is equal to r squared. So I'm going to make a substitution there. And then I have minus 6y. And then if I subtract 9 from both sides, that would just be equal to 0. Now I'm trying to get r's and thetas. I still have a y there. Well, what do I know about y? All right, so I got r squared minus 6. Y is equal to r sine theta. That's another substitution. That's that other top equation there, that r sine of theta is equal to y. So we can replace that in there. Now we just have r's and thetas left. To clean this up a little bit, because both of those have an r in it, I'm going to factor out an r. And so then there's really 2 options. One option is just r equals 0, that is just the dot, the origin dot. The other option is that r is equal to 6 sine of theta, and that's the one that would actually graph the circle for us. Okay, so we have then converted an xy equation into an r theta equation. And you could confirm that by graphing those, that they do actually graph the same thing, and you can graph polar and Desmos as well. All right, let's look at another example. Let's take the equation r cosine of theta equals -4. So this one's starting polar, and if I just say r cosine of theta equals -4, you probably have no idea of what that would possibly look like. So if we can change it into x's and y's, we might have a better idea. So how can we change this into x's and y's? Well, let's look back to those equations and see what do we have that seems familiar. Well, r cosine of theta is equal to x. R cosine of theta is equal to x. So we can make a substitution there, and we just get x equals -4. So what would that line look like? Well, that would look like that, just a vertical line at x is -4, right? Pretty simple substitution there on that one. Let's try another one. If we have r squared equals 4r cosine theta. Okay, so again, we want to look for where can we make substitution. So r squared, we see an r squared over there. Look back to our formulas. R squared is an x squared plus a y squared. So I'm going to take that r squared and I'm going to substitute or replace it with an x squared plus a y squared. And that's equal to 4, and then now r cosine theta. So let's look back to those formulas. R cosine theta, well, that's equal to x. So we're going to replace all of that r cosine theta with an x. And we've now changed it into x's and y's, and that's probably sufficient because we have changed it into x's and y's. But if I ask you, what does that look like? You probably still don't really know what the graph of that would look like. So we're going to do a little bit of algebra on this. Because both the x and the y are squared, I'm going to keep them on the same side, and I'm going to subtract over that x. I'm intentionally leaving a little blank there. We'll have it equal to 0. Now what I want to do is I want to fill in that blank, and this is a process called completing the square that you probably have memories of from algebra. I want to write this as an x minus something all squared. So to think about when we multiply out that binomial, what would I multiply to end up getting that minus 4x? And it would end up being a -2 because adding those two minus 2x's together would give us the minus 4x, and then minus 2 times minus 2 would give us the plus 4. So that's that completing the square idea that hopefully you have a little bit of a familiarity from Algebra 2. The picture I show when I teach in Algebra 2 is that we're actually going to build a square, and the idea of squares in algebra, or in geometry rather, is that the sides are the same. So what I want is what number can I put on the sides of this that will make the square the same on both sides, just like a square is the same on both sides. Well, if I have to make minus 4x's, I'm going to split those equally to make minus 2 and minus 2. So minus 2's are going to complete the sides there, but then what number completes the square? Positive 4. So that tells us what to fill in the blank. And you may be thinking, well, why do I even need to fill in the blank if we're just going to turn it into that x minus 2? Well, remember in algebra, whatever we do to one side, we have to do to both sides. So because we just added 4 over on the left-hand side of that equation, we got to make sure we add 4 over on the other side of the equation also. Otherwise, our scale just tipped. Okay? So completing the square. Back to algebra there. So yeah, y squared equals 4. Now, hopefully you recognize this as being a circle. Its center is shifted over 2 on our x-axis, and it also has a radius of 2, so it would look something like that. Okay, so started with an r theta equation, no clue what it looks like. Switched it into x's and y's, still kind of vague on what it looks like. Do a little bit of algebra on it, complete the square, and now we can recognize that as being the equation of a circle. One more conversion equation. Let's go with a fraction. Okay, so first thing that I'm going to do on this is I'm going to make it not a fraction, and I'm going to multiply both sides by that denominator. And when I do that, I'm also going to distribute the r through. So I'm going to rewrite this as 2r cosine theta. Oh, I think I was supposed to have, oh yeah, oops, sorry about that. There's supposed to be a minus between those. There we go. Okay, so then the next part's going to be minus, you're probably like, why do I need to distribute? Minus, nope, no 2 on that one, minus r sine theta equals 4. Okay, so sorry that was a little confusing because of my mistake there. So I'm multiplying both sides by the denominator, but I'm distributing through the r. So 2 r cosine theta and minus an r sine theta, and then that 4 is over there. Okay, so now I want to look for where do I have stuff that matches up with those. So we've got an r cosine theta and an r sine theta, and when we look back to those formulas, those are our x and our y. X is cosine and y is sine. So in our substitutions here, we're going to have x for the cosine and y for the sine part there. So we got 2x minus y equals 4. And now it's an xy equation, and that's really good enough as far as a conversion goes. But if we just go ahead and turn it into y equals mx plus b form, we'll add the y over there, subtract the 4 over there, and now we can see this y equals mx plus b equation. It has a slope of 2 and a y-intercept of -4. Okay, so hopefully this is pretty much a review of pre-calc and ideas that you learned there about polar coordinates and algebra with polar coordinates. And then in our next lesson, we'll look at how we can apply calculus into polar equations. Okay, as always, let me know what questions you have, and I'm happy to help even from afar. All right, talk to you later, guys.